In this video, we're going to be looking at the energy and mass balance of a cooling tower. We're going to see, using differential equations, how the water and air temperature change throughout our column, and how the concentration of the water in the air changes throughout our counter current cooling tower. So, I've kind of made a simple diagram here. This is just meant to be a cooling tower where we have some column of air traveling through with water traveling through where effectively the water would get cooled by the counter current of the air passing through. And we have some packing area over here as indicated by the lattice lines that I've made. So when we look at a cooling tower, something important to note is the packing area of it. So what I'm going to do is I'm going to make a quick little coefficient of A and say that uh, our packing coefficient in this case is going to be the surface area, so meters squared of the packing area, and the volume or the area of the what is it? Of the column itself. This will be kind of like the units for our packing, just to kind of uh, give context as to how the packing is involved with the cooling tower. So when we look at this, something that we need to break down is we need to break this down into smaller cross-sectional areas so that we can derive as accurately as we can the behavior of the temperatures and the concentration of the system. So what I'm going to do is I'm going to make a little area over here for us to look at. So let's go ahead and mark some dimensions really quick. We're going to make this side d of z. We're going to make the positive side of z go with the air in this case. This is z positive. And we're going to go ahead and label this T air out, T air in. Temperature of the water going in, then temperature of the water out. So what we need to find is we need to find the differential equations for the change of air throughout our area, or yeah, across the d of z, which is our surface. We need to find the change of temperature of water throughout our system and the concentration change c over our distance. So this will then later be used in Excel, where we're actually going to be able to compute more data for this with set numbers of the temperature and the water going in this case. So now what we need to do is we need to use some Lewis relations to relate the heat and mass transfer of the system to then give us these changes in temperatures that we want in this case. So let's go and start with the change of water. Cross some distance. So this is kind of a more common sense side of things, you could say. When we want the change of temperature of water, we have to consider the heat capacity of the water. We need to consider the area in which it's being held at in this co cooling column, right? And we need to also have we need to have some flow rate going in. So kind of going into our thermodynamics class, we note that some liquid flow rate, in this case, L, equals kilograms per meter squared second, right? So if that is the case, we can also note that for our system, there's going to be a change of there's going to be a change of flow rate as well. And so from this point, we can go ahead and relate this to the Lewis relations, which I'm going to make this smaller because we're going to write a lot for this next part. All right, so firstly, let's go ahead and do the heat transfer. So we mentioned the packing area, or the packing coefficient. We're going to go ahead and apply that here to our areas. So for heat transfer, this is going to be our packing multiplied by the cross-sectional area, which is then being multiplied by our heat transfer coefficient. And then this gets multiplied by the T air minus the temperature of the water in regards to D of Z. And then this is going to be plus the mass transfer coefficient, which is going to be Kc packing area times the actual area. And then remember to relate these two, to relate the mass transfer and the heat transfer, we put the enthalpy of vaporization on the mass coefficient to put it in joules per second so that it relates and has the same units of the heat transfer. And now we look at the concentrations, concentration of water, this concentration of air, D of Z. So something I'm going to do, this is just going to be for future computation just to make our lives easier. For the concentration of water, I'm actually going to make this the saturated pressure of water over the gas constant over T. Remember, concentration is just pressure over gas constant and temperature. So we're just going to do the same thing, but with the saturated temperature of water at this point. So to simplify this, this is pretty simple algebra. All we need to do is remove the a's of all the equations because it simplifies, and then we can just divide this by heat capacity in L and divide all others by heat capacity in the liquid flow rate. And then we can also divide all these by d of z. And now we get some pretty easy algebra. This is going to be change of T water over change of Z set equal to heat transfer coefficient multiplied by packing over capacity liquid flow rate multiplied by temperature of the air minus the temperature of the water. And then this is going to be plus mass transfer coefficient, packing, uh, enthalpy of vaporization over heat capacity over liquid flow rate, which is then multiplied by the saturated pressure of water over RT minus the concentration of air. Okay, and then we'll be able to plug this into Excel and get a general solution for the change of water across some change of distance. So now what we can do, I'm going to go ahead, section this off. We can go ahead and look at the change of concentration now. So this is going to be done a little differently. What we're going to do is we need to find a discrete velocity for our concentration here. So what I'm going to do is say 4G for the gas kind of like what this is flowing in, right? We want to know the volume in which it travels across some surface area multiplied by the time that it takes to do so. So really, this is just some velocity in meters a second, right? And so when we plug this in, what we're going to get for the change of concentration over some change of distance, this is going to be our density multiplied by our concentration in area, and then multiplied by our, I'm going to put D here, multiplied by our new velocity that we've made, right? What we're going to do is set this equal to, in this case, we only need the mass transfer. So we're just going to do our mass transfer coefficient multiplied by our packing. And then I got kind of ahead of myself, packing, and then area, and then molar, or our enthalpy of vaporization. And then I'm just going to keep this in the expanded form of the P saturation there, and then this is going to be D of Z. So can already see we can cancel out the areas here. And now we can go ahead and just do some algebra. The change of concentration per change of Z is going to be our mass, uh, our mass transfer multiplied by our packing, multiplied by our enthalpy of vaporization over our rho of G. And that's going to be multiplied by P sat of R T minus C of air. And let's go ahead and begin the next part. Now for the change of air. So find the change of temperature of air across some distance. This one's gonna be the most algebra. So this is going to be the change of, let's see, this is gonna be change of density, multiply an area, and the same discrete velocity that we had solved for earlier. And now what we're gonna do is we're gonna go ahead and relate this to our we're going to relate this to the heat capacity and temperature of the air flowing through so we can get the energy from it. So if we do the Cp of air multiplied by the temperature of air and then subtract that from the enthalpy of vaporization over our density, which is then multiplied by some concentration, we could then set that equal to our heat and mass transfer. So this is going to be our heat transfer coefficient, packing area, and then our actual area, and then this is going to be multiplied by the temperature of the air minus the temperature of the water. And then this will be plus the mass transfer coefficient, packing coefficient, area. Right, I'm not missing anything. I'm just going to look at my old notes. I'm lazy. All right, and then enthalpy of vaporization. And then this is going to be our concentration of water minus our concentration of air, d of z, d of z. Okay, so something to note here. This looks like a lot of algebra, but we actually have one very convenient conversion over here. If we multiply rho, or actually first off, we can go ahead and remove a from all of our equations. But if we multiply by rho for this function here, this actually ends up canceling out our heat transfer expression that we had just created, meaning that this is actually a redundant coefficient, and so is this observation. So the actual algebra for this is pretty straightforward because this is just results in our d change of air over d of z, which equals our heat transfer coefficient packing multiplied divided by our density multiplied by our heat capacity, and then multiplied by our discrete velocity, being multiplied by our temperature of the air minus the temperature of the water across some distance. Okay. So we now have all three of our equations that we need to observe the behaviors of this cooling tower. So at this point, we're going to be going to Excel and actually using the math here to solve what these uh to solve sorry to derive the we derived the differential equations for the water and air temperatures and the molar concentration. Now we're going to take these equations to Excel to see how the air varies throughout this countercurrent cooling tower. Stuttering my words, sorry. All right, in this part of the video that we are going to be using the equations that we've just derived for the change of temperature for water, air, and the concentration for this cooling tower. And we're now going to plug these equations into Excel. So you can see route out the equations that we'd used over here. For the change of water, I simplified it just a little bit, just for the sake of typing it in when we do it in an Excel. So it does look a little different, but the math is equivalent in this case. So just in case you have any eyebrow raises about the change of equation. So basically, the whole point of this is that we're going to try to find some temperature of the water going out of the cooling tower and figure out what the temperature would be if our temperature of the air coming in was 303 degrees Kelvin, which this was, I think, 30 degrees Celsius coming in, and then the temperature of the water coming in as well. And we're going to be using Excel Solver to kind of change some of our numbers to figure out what the temperature out would be. So To start off, just to kind of explain what these given variables are, this is our liquid flow rate of 10 kilograms per meter squared a second. This is our discrete velocity for the gas in this case. Uh, let's see here. This is the packing coefficient that we have, which is in meters squared per meters cubed. And then this is our heat transfer coefficient. This is our gas constant. When we were doing the math, we talked about taking the little, like, just a little section of the cooling towers we went throughout, and we said that that length was d of z. D of z in this case, you can imagine, like, this is like the bottom and this is the top of the cooling tower. This is the change of z throughout our system. So just to kind of explain how small that little area that we're observing is. Then we're going to figure out the mass transfer coefficient. And then we have I just Googled these in advance. These are the heat capacities of water and air. Um, we have the delta vaporization, or sorry, the enthalpy of vaporization for our system, which I also uh, looked. And then these are the Antoine's coefficients, which we're going to be using this to find the saturated pressures of our system. I'll get into that into a little bit. And then we have the density of the air going out. And then we have the concentrations for air when it's fully saturated and when it's initially going in. So let's go ahead. We're gonna go ahead and first start with the density of the air going out. So the molecular weight of air on average is about, I think it's like 29 grams per mole, right? But we're gonna put this in kilograms just so we're in the same units here. We're gonna go 0.029, and this puts it in kilograms per mole. And now we're gonna go ahead and multiply this by our pascals. And then we're going to divide. Oh, I don't think I said this equal. Sorry. Equals. And then we're going to divide by our gas constant, which I have as R. And then we're going to multiply this by the temperature coming in. And now we have the density of the air. So now what we can use this to get the mass transfer coefficient. This is going to be equal to the heat transfer coefficient uh, divided by the density of the air going out, multiplied by the temperature coming in. Oh, wait, no, sorry, not the temperature going in. This would be the heat capacity of the air. Sorry. So that's going to be our mass transfer rate, or mass transfer coefficient, sorry. So to get the concentration of the saturated air, all we need to do is we need to find the saturated pressure first using Antoine's equation. So I'm going to go ahead and do set this equal to 10 to the power of, this will be A minus uh, B divided by temperature in this case. We're going to do temperature of the air coming in minus 273. This is just to put it in Celsius, which is what Antoine's equation uses, and then plus C. Okay, so that is Antoine's equation. Now we have to convert this. Right now this is in millimeters for mercury, so we're going to go ahead and put this in ATM. So this is going to be 101,325 divided by 70. This is the conversions. And then I'm going to go ahead and put parentheses around this. And then we're going to go ahead. All right, now we're going to go ahead and divide all this by our of the temperature coming in. All right, and that should be the concentration of saturated water. And so now all we need to do is multiply this number. Okay. We need to multiply this number by the density of the air coming in. Oh, there we go. And now we have the concentration of the air coming in. Think of this as we know what the concentration of the fully saturated air is. And so getting it initially, you just multiply it by the density of the air coming in, which was given to us already. So now we have to do the Excel solver method. Excel solver works if we go ahead and guess an answer first. So I'm going to do the same one that we did in lecture. I'm just going to guess that it's the same as the temperature of the air coming in. I'm going to say that this is 303 degrees Celsius, Kelvin. All right, so from this point, we're going to be using the equations that we'd actually solve for. So this is the fun part. I'm going to do the concentration of the air coming in initially. This will be set equal to the temperature of the water coming in. This will be set to the temperature of the air coming in. Now for the saturated pressure in this case, we're just going to use the same Antoine's equation that we've been using. This is going to be 1 to the power of A minus B, which is divided by C. And then this is going to be plus the temperature of the water coming in minus 273. And then I'm going to go ahead and multiply this by 101.5 divided by 60. This is the same conversion that we've done before. Right, so that should be the saturated pressure of the water coming in. So to get delta C now, um, we're going to go ahead and take that saturated pressure. We're actually going to be going off of this equation right over here that we solved for. So this is going to be uh no, it's going to be saturated pressure uh divided by R multiplied by the temperature of the water. And then this is going to be subtracted by the concentration of the air. So we should get something like that, or the other temperature. I think that's right for now. Okay. So this is going to be the very long equation, the reason why I simplified this equation just a little bit. So to find the change of the temperature of the water, we're going to go ahead and plug in the equation that we had solved for. So this is going to be the heat transfer, oh, sorry. This is going to be the heat transfer coefficient multiplied by the packing coefficient, divided by, let's see here, divided by the heat capacity of the air, multiplied by our liquid flow rate. All of this gets multiplied by the temperature of the water minus temperature of the air. And now we're going to go ahead and add the enthalpy of vaporization multiplied by the packing coefficient multiplied by the heat transfer coefficient. And then we are going to divide this by the density of the air. Oh, density of the air coming out, sorry. And then multiply that by the heat capacity of the air. And then multiply that by 1 over the liquid flow rates multiplied by the heat capacity of water and then multiply that by the change of concentration. I am suspicious of one of these values. I think I may have done some algebra. Problem is that I think the P saturated might be a little bit too high. I was a fool. I accidentally set this to temperature of the water coming in instead. So this is supposed to be 303 to temperature of the water going out in this case. So that's why these numbers were unusually high for the part that we're at. So from this point, we could plug in the rest of the equation. However, this is actually, no, wait, no, I forgot. From this point, we just go ahead and plug in the rest of the equations. The change of concentration is going to be I need to make sure I'm in parentheses here. Mass transfer coefficient. Let's see here. Let's see. Okay, I found the mistake that I made. I just forgot to set this to the temperature of the water coming out. So the numbers were just a little higher than I thought they were going to be, but we're fine from this point. So we're going to go ahead and solve for the change of concentration of air now. So we're going to go ahead and type Kc multiplied by the uh, fucking coefficient. And then we're going to go ahead and what is this? We're going to go ahead and divide this by G and then multiply by delta C. All right. And then to get the concentration of the air, it's going to be done the same way. That's going to be Kc times A divided by G. And this will be multiplied by the change of temperature from the water minus the air. Oh, did I forgot to put a period there. There we go. Okay. So now what we're going to do is go ahead and we're going to use Euler's equation to kind of give the initial values or to fill in the values for the rest of the temperatures here. So this is going to be set equal to the temperature above plus d of z multiplied by the change of air in this concentration of air. So we're going to do that. And then this is going to be set equal to that plus d of z multiplied by the change temperature of water. And then this will be 103 plus d of z multiplied by our change of air. So now what we're going to go ahead and do is fill in the rest of here. Then all goes right. Let me check the initial values. Okay, these look good. We're going to go and fill these in. Okay, so now we have some changes of temperature happening here, right? Something I'm going to do is I'm just going to very quickly look at the temperature of water really quick. No, 1003. Okay, that looks right. So because we're using estimations with Euler's, there's kind of a part with Excel where this data just kind of explodes because we just put in a guess. We don't actually know the actual value. So if we look, temperature of water looks normal, it's rising normal. And then look, we went from 364 to over twice that in not even 10 steps. So at this point, what we can do is say we have the amount that we have grown, and we want to look for some desired temperature out. So for the desired temperature out, what we want is the temperature of the water coming in. So we want to say that our desired temperature is 323 in this case, right? So let's say this equals, we're going to do a sum squared really quick. We're going to do 3 minus this value, power of 2. Okay, so now what we want is we want to go ahead and set this as an objective and have this set as a changing parameter. Oh, wait, actually, this is supposed to equal uh, temperature out, just to make sure that this can actually change the data. So what we're going to do is we're going to take this value. We're going to go ahead and go into data. We're going to go into solver. And we're going to go ahead and say we want the minimum of this and that our the value, oh, come on. And that we're going to do this by changing the temperature of the water coming out. So when we press solve, oh, okay, something happened. Okay, sorry. I was having issues with solver again. So what we're going to go ahead and do is the whole goal of this is that we're going to try to minimize this value by changing the temperature of the water coming out. And so that will allow us to find the actual temperature going out of our system. So we wait for solver, and you can see this is very close to 300 degrees Kelvin. So this is about the temperature they would want. And if I go all the way down here, look at that. We get 300, almost 323 for the temperature of the water at the very bottom, which is very close to what we had over here, temperature of the water coming in. So this is how we use the changes of water, temperatures of water, concentration, and air to solve for the missing temperature value for the cooling tower for water in this case.